We're on 6.2, using proportions to solve geometry problems. Remember in 6.1, we learned about proportions and a reminder algebraically how to solve them. So now we're going to bring them into more of our geometry problems. Okay, 2 vocab today. One is scale drawing, a drawing the same shape as the object it represents, just a different size. One of the famous scale drawings that most of us are familiar with is a map. So it takes a big area and it reduces it down to a very small size so that we can look at that. Okay, but don't forget, you also see scale drawings in biology where you might see a drawing of a cell. Well, a cell is a very, very tiny object, and then we blow it up so it's bigger so we can actually see the details of it. So our scale drawings can be bigger or smaller than the actual object, okay? Scale is a ratio that describes how the dimensions of this drawing are related to the actual dimensions of the object. Okay, so important that we can know the difference between scale and ratio. On a scale, and we'll talk about this more, it's going to have different units, okay? And if you think about it, especially when like on a map, our scale often is like 1 inch is like 50 miles or something to that effect. We wouldn't want them in the same units because we wouldn't be able to comprehend really what that really stands for. If we try to do 1 inch into how many inches are in a mile or 50 miles, that's crazy because it's like 5,280 feet. So multiply that by 12, for inches, and then times 50, it would just be crazy to try to put all your scales in the same units. So we often use different units in a scale. You don't have to, but we often do, and it's okay to do that. This is different than a ratio, okay? It's a type of ratio, but this is different than just that one ratio. All right, let's talk about just some properties of proportions before we start. And my key theme when we talk about this is simply to tell you there's more than one way to set up a proportion and to still get the same answer. So the big idea here is your proportions do not have to look like your neighbor's proportions, and you can still get the same answer. What's important is that you organize them in an organized fashion, and then you get the answer. Just a key, you can set up proportions all day long, and you will always get an answer. But you have to set up your proportions correctly to get a correct answer. Okay, so the first property we have here is called the reciprocal property. And it says if you have a proportion that's already equal, if the two ratios are equal, then their reciprocals are also equal. So if we had A over B equals C over D, then B over A is going to equal D over C. So we can just flip both of them. And we still get equal ratios, but they look different. For number 3, if you interchange the means of a proportion, then you still have another true proportion. So remember, the means are these middle ones. It says let's interchange them. So A over C, and let's put B over D. So we just switch what's in the means, and it's still a true proportion. The last one says in a proportion, if you add the value of each ratio's denominator to its numerator, then you have another true proportion. So on the first one, I had B in the denominator. So if I add A plus B over B, I add on the second one its denominator C plus D over D, and I still get a true proportion. Okay, I see the rules. Okay, let's look at it with some numbers so you can see that this is going to make some sense, okay? So let's go to page 2. And we're going to look at each of these properties with the same set of numbers. Okay, number 1, they give us a true proportion. They already told us in this diagram, AC over DF equals BC over EF. They already figured out it's true. We don't have to worry about it. So if you see AC over DF, AC was 12, DF was 18, equals BC. Well, BC over here is 9 over EF here, which is X, okay? And just so you can kind of see this reference, if I multiply my extremes, I'm going to get 12 times X equals, when I multiply my means there, 18 times 9, okay? I'm not going to leave it like that, but I want you to see it. Okay, the reciprocal property says I can flip both of my fractions, and I should still have the same thing. So if I flip 12 over 18, it becomes 18 over 12. If I flip 9 over X, it becomes X over 9. Okay? Let's do a multiplication here. So I multiply my extremes, I get 18 times 9 equals, I multiply my means, I get 12 times x. Well, is 18 times 9 equals 12 times x the same as 12 times x equals 18 times 9? Definitely. So it's still the same thing, just written differently. All right, let's do the interchange the means, which means I'm just going to switch the means out. So the 18 and the 9, I'm going to switch spots. So 12 over 9 equals 18 over x. Okay, again, to see if this works, let's do a little cross multiplication. I get 12 times x, that's my extremes. 9 times 18, that's my means. Is 12 times x equals 9 times 18 the same as 12 times x equals 18 times 9? Definitely. So still the same. All right. One more to go, and this is the hard one, the one where you add its own denominator to the fraction. So I get 12 plus 18 over 18 equals 9 plus x over x. Okay, it seems silly, but it says to add its denominator to the numerator. Okay, let's do some math here and see what this gives me. I get x times 12 plus 18 equals 18 times 9 plus x. Okay, seems funny. I'm not going to do my math here. I'm going to just distribute. So I'm going to get 12x plus 18x equals 18 times 9 plus 18 times x. So that's when I distribute, right? Okay. It looks like I can subtract an 18x off of both sides, and they cancel, and I get 12 times x equals 18 times 9. That's what I started with, right? 12 times x equals 18 times 9. So throwing some values in here, we can see this is still the exact same thing, whether we do the reciprocals of both, whether we interchange the means, whether we add its own denominator on, we still get the exact same values, okay? Again, key idea here, we can have different setups for our proportions and still get the same answer. So don't worry if your work looks different than your neighbor's. If you both set them up correctly, you'll both get a correct answer. Okay. What's nice about most of our work today is we get to, they're going to do the setups for us. They're not making us think too hard yet. So you're often going to get your geometric ratio set up for you. So we're doing a lot of plugging and chugging today, okay? Kind of easing us back into this math stuff. So we get JL over LH equals JK over KG. So that's our proportion. We're going to solve for our missing values. They want us to find JH and JL. Well, right now JH has this big X on it and JL has nothing on it. So we need to figure out that X first. Okay, let's plug and chug. What is JL? Well, J to L, oh, there's nothing marked there. The whole thing is X and the bottom is 2. If I told you that x was 10, how big would JL be? It would be 8. How'd you get that? 10 minus 2 equals 8. What if I told you that x was 25? How big would JL be? 23, because you would do 25 minus 2. So whatever that x is, you subtract 2 from it, right? So let's just call it that, x minus 2. Okay, because whatever x is, we'll subtract 2, and that's what's going to get there. So, and we don't know what the x is, so we can't really make up our own number. Okay, so we're going to call JL x minus 2 over my LH, having trouble here, LH, which was 2. And JK is 15 there, and KG we know is 5. All right, there's our setup. It's a proportion, time to solve. Multiply my extremes together, so 5 times x minus 2. Multiply my means, which is 2 times 15. Distribute, I get 5x. 5 times negative 2 is negative 10. 2 times 15 is 30. Add 10 to both sides. I get 5x equals 40. Divide by 5 and x equals 8. All right. So x equals 8. So this big thing is 8. So that's JH, right? The whole thing. And then if I do 8 minus 2, I get 6 for the short part. Okay, that works. It's nice that they set it up, and then I just had to figure out that little bit of algebra in between. All right, in example 1 up there, where we did all 3 of those examples, find the value of x. Well, I think it doesn't matter which one we choose. Didn't we see like each time 12 times equals 9 times 18? I kept seeing the same thing over and over. So 12x, 9 times 18, 162. Divide that by 12. And, oh, I didn't even get a whole number. X equals 13.5. I'm trusting that it's the right thing, though, because we found the same setup 3 different times, right? All right, back up here on example 2. They gave us a new proportion. They want us to solve it. KL, that's 12. Don't mind me. Over GH, I don't know GH. I'm going to call it Y. I don't want to confuse it with that X that's already there. JK is 15. JG. Okay, careful. We don't have JG, not as one number, but we can add those two together, right? So 15 plus 5, that's like 20, right? All right, there we go. So now we're going to cross multiply. 12 times 20 equals Y times 15. 12 times 20, that's 240, equals 15y. Divide by 15. 240 divided by 15. I got 16. All right, so that must be my GH, right? That one I was missing on the bottom is that 16. Okay. Let's move on to page 3. All right. Number 3 here. Something I want to stress to you when we deal with these scales. When we set them up, we need to kind of follow the same pattern. So we're going to set up image over actual every time. And if you think about it, that's usually how your scale is when you go to a map. The image would be how big on the map. So like 1 inch equals like 50 miles, okay? So the actual's on the bottom, the image is on the top. And I want all of us to follow that same one because then as we talk about it, we'll have the same thing. So image over actual when we write a scale. Okay, so some key things. You can leave units on the scale, and they can be different. We kind of talked about in the definitions, okay? We want image over actual. We're going to leave the units on there, and it's okay if they're different. And as a hint, I'm going to tell you to divide by the smaller of the two numbers to get your scale. What that's going to do is one number will always be 1. And it might mean the other number's a decimal. So it's okay to have a decimal. Okay? Just a reminder from 6.1, it was not okay to have a decimal in a ratio. We always said reduce to lowest terms, but don't turn them into decimals. But on our scale today, it's okay to have that. It's okay to have a map that it says 1 inch is 75.5 miles. It's not likely, but it's okay. There's nothing wrong with that. So we can be different units. It can have a decimal, but it's really nice to have one of our units be 1. Okay, so let's try it with this first one and see if we can kind of follow the rules. It says the length of the key in the scale drawing is 7 centimeters. The length of the actual key is 4 centimeters. What's the scale of the drawing? So this picture we see right now is bigger than what our normal one is. Okay, so our scale is going to be a little bit different because of that. Okay, key thing, we're always going to put, find the scale, write the ratio of the length of the drawing into the actual. Okay, length in the drawing, that's the image, to the actual. And then rewrite the ratio so that one number is 1. Okay? So length in the drawing, that's the image over the length actual. Okay? So in the image, mine is 7 centimeters. Actual, it's 4 centimeters. Key. I don't care what the units are. Ignore them, but leave them there, okay? So we write them image over actual, and we divide by the smallest number. So because my smallest number is 4, I'm going to divide by it. 7 divided by 4, not real pretty, 1.75 centimeters. 4 divided by 4, well, that's obviously 1 centimeter. So that's my scale, 1.75 centimeters to 1 centimeter, okay? Let's try it again. For number 3, in example 3, suppose the length of the key in the scale drawing is 6 centimeters. Find the new scale of the drawing. So always image over actual. We're going to always stick to that. So the scale drawing now is 6 centimeters. I know my actual length was 4 centimeters. We don't care about the units. We just leave them. We divide by the smallest number. 6 divided by 4, 1.5. It's okay to have decimals here. Always leave the units. 4 divided by 4 is 1. So now my scale is 1.5 centimeters to 1 centimeter. Okay. So what I'm doing today is different than what I did in 6.1. So the ratio, kind of comparing here. Ratio needs the same units, no decimals, final answer has no units. Okay? So on that one we reduce, right? No decimals, and all we do is reduce to lowest terms. Okay, on the scale, it's okay to have different units. It can have decimals. Final answer includes the units, okay? So on this one, we divide by the smaller number, and one number is 1 every time. Ratio versus scale. They're very different, even though they could use the same numbers, okay? What you're going to see, though, is going to look different. All right, let's look at this story problem here. Using a scale drawing. On this map, the scale of the map at the right is 1 inch is 8 miles. Find the actual distance from Westbrook to Cooley. It says use a ruler and find the distance from Westbrook to Cooley on the map. Okay, so if you get out your handy dandy geometer, you have a nice ruler. And we have to think, though, which side of the ruler do we use? Well, because my scale is in inches, I need to use the inch ruler. Okay, so if you get out that handy dandy, and by the way, when you measure, you kind of have to go like straight across. You can't really, I mean, you could go down there to that where intersection and then back up and measure. I'm going to tell you, I'm measuring about 1 1/8 inch. Okay. Now, we have a problem, though, because I don't want a fraction in my proportion, which is fractions, right? I really don't want a fraction in a fraction. Okay. So, by the way, we have image over actual, right? So my image is 1 inch to my actual, which is 8 miles. Notice I'm kind of using words just like I did on the story problems from 6.1. Okay, I'm looking for how far apart they are actually. And I had 1.18. Okay, 1 1/8 inch. So if I do 1 divided by 8 on my calculator, that's like 0.125, and then I just put the 1 in there. So I'm going to put it 1.125 inches. All right, cross multiply my means together. X times 1 is just 1x, and 1.125 times 8, and I get 9. So it looks like I'm about 9 miles apart between those two. I might be a little bit off. Notice the word about, because if I measured a straight line versus if I tried to measure kind of section to section, but it gives me a general idea using my scale. All right, last page of our notes today. You buy a 3D scale model of the Sun Sphere in Knoxville, and the actual building is 266 feet tall. Your model is 20 inches tall. The diameter of the dome on your scale model is about 5.6 inches. What is the diameter of the actual dome? Okay, B asks a totally separate question, so I don't want to look at B right now. We're going to just look at just the A part first, okay? So just the A. Okay, image over actual. And just kind of so we're keeping straight, on my image, which is the model, right, because it's not the actual thing, I have 20 inches tall, and my dome is 5.6 inches. So my image is my model, right? And I want to find out, I'm talking about my height, and I'm talking about the diameter. So I'm just kind of keeping words here so I keep track. So on my model, I'm 20 inches tall, and I have a 5.6 inch diameter. So on the actual, I have 266 feet tall, or height, and I don't know my diameter. So I put an X there, and I have the setup. All right, multiplying here. And by the way, it's okay if our units aren't the same, as long as going across I'm inches and going across I'm feet. I'm good, and I need to know that my final answer will be in feet. Okay, so my extremes, 20 times x is 20x. 266 times 5.6 is 1,489.6. Divide that by 20, and I get about 74.48. I'm going to round it to about 75 feet tall, okay? So that's the actual, right? About 75 feet high. All right, set it up with your image and your actual and go from there. Okay, this second question is extremely different than what we just did. How many times as tall as your model is the actual building? If we're trying to figure out how many times taller it is, we have to be in the same units this time, okay? So this is walking away from the scale a little bit, kind of going back to our ratio from 6.1. We have to be in the same units. So right now for my height here, I have 266 feet and 20 inches, right? And actually, to be honest, that's like actual over image right now because they ask us for the model and the actual building. So we just need to know that. Okay, once again, same units. So always easier to change the big units, which is feet, to the inches, okay? 12 inches in 1 foot. So my feet cancel. I multiply across the top, 266 times 12. And that's 3,192 inches compared to my 20 inches I had. Now that they're the same units, they don't matter. If I do 3,192 divided by 20, 159.6. Let's round that to about 160. So I'm about 160 times taller in real life than what I was with the model. Okay, very, very different question on B because you have to be in the same units to compare them versus we can work in different units when we have the scales, okay, to find missing parts. All right, for number 4 here, two landmarks are 130 miles from each other. The landmarks are 6.5 inches apart on the map. Find the scale of the map. So scale is always image over actual. So my image on the map is 6.5 inches. My actual is 130 miles. Remember, I don't care if they're different units, that's fine. I simply set them up image over actual and divide by the smaller number. So 6.5 divided by 6.5, well, that's easy, it's 1 inch. 130 divided by 6.5, 20. And 20 miles. It's good to be in different units. It's okay to be in different units. I want one number to be 1, and I leave the units on it. I'm good. There's my scale, 1 inch to 20 miles. All right, and to finish us out, your friend has a model of the sun sphere that's 5 inches tall. What's the approximate diameter of the dome on your friend's model? So now we're comparing my image over my actual is going to be my friend's model to the real one, right? So I'm talking tall, and I'm talking diameter. I guess I could have called that height again, right? Okay, so the model's height is 5 inches. I don't know its diameter, but I know it's going to be in inches when I get done. The real one was 266 feet tall. And we solved earlier and found, let's just call that diameter 75 feet from earlier. I don't really want to work with it too much of a decimal. And again, it's okay to work in different units as long as across they match, okay? So we're ready to go. I get 75 times 5. I get 266 times x. 75 times 5 is 375. Divide that by 266. Just a hint, I don't think it's coming out equal. Or a whole number, I should say. How about 1.4? And I look back up there, it's going to be in inches because that's what spot it was in when we were solving for it. So at about 1.4 inches for the diameter on that friend's model. All right, so we're doing a lot more of the proportion work. Now we're adding it to these geometry problems. And just be careful on the scale. Different units are fine. Set it up image over actual and divide by the smallest number. So we're back in our books again tonight, page 367 to 368, 3 through 18 all, and 22 through 24 all. Please show your work. It's a lot easier to check when we see where you found your answers at. And the back of the book and Slater don't count. Let me know if you have any questions.